In this section, what you should have noticed is that with each subsection within the section, we're going back to the original problem. We're just adding one step. And in this case, we're throwing what we had outside of the radical under the radical, and we have to simplify each radical even further before we can simplify the expression. With our first problem, part A, we're given the square root of 32m to the 7th minus the square root of 50m to the 7th. So let's first off factor out any perfect squares. So what is the largest factor that is a perfect square? Largest factor of 32 that's a perfect square would be 16. And then we're taking the square root, so we want the exponent to be even on the variable, so m to the 6th. And what are we left with? We're left with the square root of 16 times 2, so the square root of 2. And then m to the 6th times m would give us m to the 7th. So we're left with the square root of 2m. Minus, what's the largest factor of 50 that's a perfect square? That would be 25. And again, because we're taking the square root, we're the index is even. We want m to the highest even power less than 7, which would be m to the 6th. And then again, what are we left with? Well, 50 divided by 25 is 2, so we're left with 2 under the radical. And then m to the 7th divided by m to the 6th, we're left with m. So again, we're left with the square root of 2m. Now we simplify what will be the coefficient, or will be outside of the radical, outside the like radical of square root of 2m. So the square root of 16m to the 6th, that square root of 16 is 4. The square root of m to the 6th is m cubed. And again, we're left with the square root of 2m minus, this is going to simplify, square root of 25m to the 6th is 5m cubed. And again, we still have the square root of 2m. And now we have like radicals, and we can simply subtract what's outside of the like radical. And again, I'll factor out the square root of 2m so we can see what we're doing. This is 4m cubed minus 5m cubed times the square root of 2m. 4 minus 5 is negative 1, so we end up with negative m cubed times the square root of 2m. Similar process with part B. It might be a little bit more difficult to recognize what the largest perfect cube is that's a factor of each value. But we're given the cube root of 135x to the 7th minus the cube root of 40x to the 7th. So if we looked at all of the factors of 135, we would see that 27 times 5 is 135. 27 is a perfect cube, so we're going to have the cube root of 27. And then again, we want what's the largest exponent less than 7 that is a multiple of 3? That would be 6. So cube root of 27x to the 6th. And then what are we left with? That's going to be the cube root. 135 divided by 27 is 5. X to the 7th divided by x to the 6th is x. So we're left with the cube root of 5x. Minus 8 times 5 is 40. So 8 is a perfect cube. And therefore, we have the cube root of 8. And again, x to the 6th, because that is a multiple of 3. 6 is a multiple of 3. And we're left with 40 divided by 8, cube root of 5. And x to the 7th divided by x to the 6th is simply x. Now we simplify what we factored out, or what we took separated from each radical. The cube root of 27 is 3. The cube root of x to the 6th is x squared. We're left with the cube root of 5x minus the cube root of 8 is 2. The cube root of x to the 6th is, again, is x squared. And we still have the cube root of 5x. Now we have like radicals, cube root of 5x, cube root of 5x. So we can subtract what's up front. 3x squared minus 2x squared times the cube root of 5x. And then 3 minus 2 is simply 1. So this is x squared times the cube root of 5x. And if we wanted to check these, we could use, I wouldn't use 0 or 1, but we could use any arbitrary value for x and verify that our original ends up yielding the same numerical values as our solutions, our simplified versions of each expression.